Okay? And anybody from this characteristic equation, how to find the poles of the system? Alright, so you solve
The root.
Okay? Right. So ds equals 0, it gives you a polynomial in S. When you solve this polynomial, you will find the poles of the system. This polynomial, right, the order will be the same order as the order of the system. The third order, it will be S to the power 3. Then you have 3 poles. Okay? So this is what you have done so far. And then last week, I introduced you to the fact that from the state space system, you can also derive the characteristic equation without going back to transfer function. And everybody can tell me, if I've given you the state space representation for any system, that means you know the A, B, C, D, how do you find the characteristic equation? How to find the characteristic equation for this one? So how to find the CE for this one? In terms of A, B, C, D. Just now somebody shouted off the somewhat the correct answer. Eigenvalues, right? Eigenvalues of what? So eigenvalues are reserved for matrices. A, B, C, D are all matrices. So you want to find the eigenvalues of A. So to find the CE, you'll find the eigenvalues of A, which is found by finding the determinant Si minus A. This thing means determinant. So Si minus A, you find determinant set to 0, right? You will get a polynomial in S also. And then anybody can tell me how to find the poles for this system? For the state space? Solve now, you solve this one. Okay? So if you have this grid system, you describe it with the blue way and the purple way, the answer below is the same. Because you're still finding the same thing. Right? So that means if your system can be expressed in this form, when you find the CE and then solve for S, this pole will be the same as the CE and pole location if you actually express it in state space. Okay? Okay? So again, very important, because we always want to know about the CE. The CE is very important because it tells you about the stability, or whether the system is stable or not. Right, so the key part is whenever you give a system, you always want to know the CE. Okay, so maybe I will write something here. CE is for like stability and also transient response, like how fast the system, right? It depends on where the poles are located. Right? Further left, fast, closer to the imaginary axis, slow. Then if you cross over the imaginary axis, you become unstable. Right? So that's why the CE is very important. Because the CE gives you the pole location value. Okay, so this is what we did last week. Right? So again, just making sure you remember, maybe I write here, this thing is the determinant. Si minus A, then you find the determinant of the thing. So 2 by 2, there's a method, 3 by 3, there's a method. Fine. Okay, so today, as well as tomorrow, we will go into controller design. So this system here, if you're given the GS equals YS over US side, to design a controller, you can do something like this. Right? Something like this. Have you seen this before? Of course, you definitely have. You've seen this in the PID note. You've also seen this in the DC motor PID controller lab 4. So the GS is the system, and then your controller is the GCS. The controller is very simple. What it does, it reads where you want to go, which is RS, subtract off the YS, which is where you are, which gives you E, and then the error is being applied from. So in the Laplace format in domain, the GCS is KP plus KIS over plus KDS. This is what you learn. Right? If you're wondering, where have I seen this? I don't remember seeing this. I will recall the notes for you. It is right here in PID notes. Right? So this part is focused on this guy only. Right, so the controller, right, the input to the controller is E, the output controller is U. Then it goes into the system and interacts with it. Right? And the one on top, the GCS, that's the Laplace representation of the PID controller. When you implement it, you don't implement in Laplace. You will normally implement it in the time domain. So the expression there, if you here, if you do the inverse Laplace transform, you will get to this expression, which says that the output U, means the thing going to the system, which is output the controller, is just a combination of three terms. The error multiplied by Kp, plus the error that's integrated from time 0 to infinity times Ki, plus Kb and the rate of change of the error. Right, so if you were to implement a controller in real time, like in your Arduino or the DC motor, you will be using this. And all you need is just the error. And then this error, you either multiply it with a gain, called the proportional gain, to integrate the gain. Integration is relatively simple, you just add them together. You can do numerical integration. And the last one is you differentiate it. You see how fast the error is changing and multiply it with two gains, Ki and Kb. And that was how we found or derived the PID controller. And then the key part was finding Kp, Ki, and Kd. And there are a few methods to do so. You can, if you know the system, you can find the best Kp, Ki, Kd directly. I'm sure you also tried that. You can also experimentally tune it. Okay? And also the Ziegler-Nichols tuning method as well. Okay? All various methods of doing tuning. Yeah, so this is the traditional way, the classical way of controller design. Again, it's very limited because you realize that there's only one input and one output. Right? Because you can only compute the error for one variable. So for the DC motor control, it's okay because there's only one thing spinning. Once you go to the inverted pendulum, there's both the arm and the pendulum angle. And it's not so easy because now I have actually two errors. The error is pendulum angle and the error in the arm angle. And the conventional way is very difficult for me to do so. Right? So this is where feedback control for state space is a little better. Because state space is really designed for multiple input, multi-output. You can use the expression to design controllers in that form. So not to say PID is no good. PID is still very good. It's one of the most popular ways to design a controller, but it's not the only way. Today I will show you another way using the state space control. And it's called full state feedback control. Okay? And as the name suggests, we will use the states for feedback. Very similar. Once I show you the diagram, it will be quite similar. So now when we do the control, right, we have to introduce two words right now, open loop and closed loop. So open loop means no controller, closed loop means with the controller. So the diagram there is a closed loop diagram, right? So this is under closed loop control. Well, the diagram on top here, maybe as a very good, maybe revision to make sure you understand this for your final. Can anybody tell me what is YS over RS? For this one. So, and then before you tell me the numerical value, can you tell me the name of this thing? There's a name for this expression. CLTF, it stands for the closed loop transfer function. Okay, now we go on to the important part. What is the expression for the closed loop transfer function for this system? So here your thing is the GCS, GS divided by 1 plus GCS, GS. Right? Okay, let's see how many of you understand this. Can you tell me the closed loop characteristic equation? So how many you think about it? Just now you tell me the correct answer already. Now I want the closed loop characteristic equation. So use the same thing you tell me. This one, many of you are very good. Denominator set to 0. The important part is which denominator right now. And so the denominator right now for the closed loop system, remember this is this one here is the closed loop transfer function. Right? Let's use another color. This one here, this thing here set to 0. That is the closed loop characteristic equation. Make sense? So because of this, now that the closed loop characterization is 1 plus GCS GS, you will see that now the GCS will affect the pole location. Previously, it was just the denominator of GS. That was the poles of the open loop system. It means when you don't do any control, the system stability, how fast is it, where is it, is governed by this CE. Once you construct this feedback diagram, the whole dynamics changes. First, the whole transfer function used to describe the system used to be just YS over US. Now is this expression. And because of that, if you want to find the CE for this closed loop system, you will find the closed loop CE. And then when you solve the closed loop CE, solve for S, what do you get? If you solve the 1 plus GCS GS because you solve it, what do you get? You get the closed loop poles. Same as below. So the only difference right now from the top part and below is that the top part, we call them all the closed loop stuff. The bottom is open loop. So same for the state space. Previously, what you're doing here to find SI minus A, so for this side, that is the open loop characteristic equation and the open loop poles. Okay. So today we will introduce you a way to do control for the state expression, and this is called the full state feedback control. Okay, it's very simple, and let me my remark here. Right, so this system here, the one on top here is this base system. You don't do anything. Essentially, it's U go in, then the X go in, out come out is UY. And then the CE is SI minus A equals 0, should be this factor. So today, I will introduce you the control for state space. Right? So for this system here, the key part here is expressing the system in the closed loop transformation, right? So we sort of need to do it here. For the controller in the transformation, right, it's sort of like a PID controller. Actually, it can be anything, but as long as you put it in. For state feedback control, I'll draw a line here. Right. The control law is very simple. What we're going to do is now the U we actually multiply by this. Okay. This seemingly very simple expression with only 3 variables is called state feedback control. And with this, you can stabilize the system in state space form. So let me show you what's happening. So here previously it was this here. So what we're going to do is right now from the X here in between, we'll read out the X. So the X is the states of the system. X1, X2, X3, X4. What we're going to do is for every state, we will assign a gain called K1, K2, K3, K4. And then we'll multiply it and then insert it back into the input. We're sort of trying to recreate this. Okay? We're trying to recreate this. Because we know that feedback systems can stabilize systems, can improve the performance. So we want to try to create like a feedback architecture for state space. As you know, state space is slightly different. The only difference is the X here is the vector. Previously in our block diagram here, everything here is this one scalar. But once you go into X here, this is a vector. Okay, so the control law is U equals minus Kx. You can expand it out as, right here. You can expand this out as K1, K2, all the way to Kn, multiplied by X1, all the way to Xn. Right, and when you multiply out, you get that. Yes?
Previously, the input is U, and now the input will be R.
Yeah. Same thing is really here. Previously, the input is U. And once you do control, we have a preference. Then you replace it right here. Closed loop characteristic equation. Is it ES over RS? can, but nothing here is about steady state error, but you still can. Yeah, here I only concerned with the closed loop poles. You can actually find the expression for the E, and then use that to find the steady state error, which is asking your part. I did not put it in because that's not the main part of this topic today, but you can. Back to the question, you get it? You have a system, and then once you apply closed loop control, your input changes because it used to be input the system, now you set a reference.
So the input, the U is always input to the original controller.
Yes.
Then R is just the new input with the controller. But why is the R is?
I'll get to that. I haven't get to that. Yeah, I haven't get to that. Alright. Yes, another question. Where's the negative sign? Okay, you are right. Okay. Sorry, thank you. Okay, U equals minus kx. And then k is a vector with all the smaller k's, k1, k2, all the way to kn, and then the x is x1 all the way to xn. So back to the question because you asked about why the R is 0, I haven't got to that. So typically in your PID controller, this R can be anything. Step control, can be RAM, can be actually anything you want. But for state feedback control, I will make it a little easier for you. We will do what we call regulator control. When we say regulator control, we assume that the R is 0. And the reason for this is quite simple. If you can get the system to go to 0, that means you can get the system to go to any number you want. Because 0 is just a number. I can just offset it. You can go to 2, 3, 4, 5. Okay? So this is called regulator control. Making a system go to 0 is called regulator control. So that's why for state space here, to make it easier for you, we just set R to be 0. You can make it not R not 0, just that the analysis is a little more complicated. To make it such that you're beginners, you make it R equals 0. So the goal for the system in regulator is to make sure that all the system goes to 0. All the states go to 0. And again, to repeat this, if you can get the states to go to 0, then means you're well capable of making the system to go to any number you want. Sorry? It's actually more because it's persistent linear. You can go to 0, you are perfectly fine to go to any number you want. Okay, so what is going to change is right now is that I want to have some space here. Okay, so now U equals minus x. So the only difference right now is that now with U, it's going to be can be written in terms of x. So what we're going to do right now is I will erase this part here, so I have some space here. Okay. So I will rewrite what we're going to do right now. It's going to be U is equals to minus x. Okay. So how does this change the space system? Because previously what we did was we multiply A here, we found the closure transfer function, and it changes. We want to know how this expression changes the system. Okay, and all you need to do is you substitute this into here. And let me do it with you. So if you do the substitution, you will get x dot equals to ax plus b minus kx. Because u equals minus k. With this, you can expand out, you get ax plus x plus. Right? And then I will collect the term because both of them have x. So I collect the term. I will get a minus b k x. Okay. So what I'm going to do next is to help you see what I'm going to suggest next. X dot, right? I can say that this whole thing is x bar x, where x bar is a minus b k. Do you agree? At this junction here, I want to see how good many of you are using. At this junction here, can you tell me for this system here, this expression here, after substituting with this, Can you tell me the characteristic equation for this system? You told me just now that the CE is SI minus A, right? For the open loop, for that expression. So now, maybe for those who really want it, technically is 0U. Okay? Technically, that's how it looks like. So B is 0 in this case. Can anybody tell me the last line here? If you want to find the CE for this system here, what will it be? So SI minus A bar. So the CE will be SI minus A bar set to 0, right? And because this is a what we call closed loop configuration, this will be the closed loop CE for the system under state feedback control, under full state feedback control. That makes sense, right? If you have a system in state space form, you want to find the CE, it's SI minus whatever the A is. With U equals minus Kx, the A has changed from A to A minus BK. Yes. 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 Okay, so on top there is what we did last week. The bottom part is what we're going to do this week. And what we do this week, basically just let you, the input resistor, now you let it as a multiple of K times X with a minus sign. And once you do that, you substitute in, you'll find that now your CE, the classification which defines how stable, how fast system, is now SI minus A bar. And A bar consists of A, B, and most importantly, K. So that means the pole location, where to place the pole, where to put the pole, you can modify it with K. Same as what you did for the PID controller here. Right? So the C, closest C for the PID controller has this GCS inside. GCS inside has KP, KI, KD. So if you change KP, KI, KD, you can change the poles of the system. And that's what you did in the DC motor controller, right? You change the KI, KP, KD, you change the system response. You never physically change the DC motor to your gate, you didn't unscrew this, you didn't do anything, and you only electronically modify the response. Same for the state space, saying that you can also do the same thing when it's in state space form. Okay? So on the bottom right there, you realize I have this expression here, that the CE is SI minus A minus B here, and how to get that is because A minus BK is A bar. Okay? If you can get this, the rest of this week is smooth sailing. All you need to know right now is how to find K. Right? But essentially, it's just implementing this similar to how we implemented the feedback controller for the PID controller. Right? See? What's the significance of the what? So controller means what is the value for you. So for PID controller, PID, this is the controller. This guy is the controller. Controller means if you were to implement the controller, what is the mathematical expression? So for PID, it's KPE. This. The controller for the state effect controller is actually even easier. It's just minus KX. That's it. What is what? It's literally the simplest way to implement a pure control. You just read the state, multiply again, and feedback. Yeah. Because for feedback controller, you need to feedback what's the current state, literally, right? That's what the premise of feedback controllers in this form. You read whatever the state and read back so they can have an error. Same thing here. You're actually reading out the errors for all four states. Again, remember we're doing regulator. We want all the states to go to 0. Okay? Again, because if you can bring all states to go to 0, you are perfectly able to bring all the states to any number you wish. Yes?
Is this supposed to be like something minus kx, because we said r to 0?
Yeah, essentially it's something minus, but now it's 0. So 0 minus this is minus kx. To make it easier for you, set r to 0. but you can think of it as R minus this thing.
So if you want to change like our target, then like it won't be so.
If you want to do it, yes, you can't take advanced control 30.14. For now, we do simpler for you. Set it to 0. Go make sure you can understand the go to 0 first. Yeah. I know you're very eager, but I must slow you down. It's not your go beyond yourself. Yeah, again, so again, R is 0. So we want the goal of the system is to bring the state to be 0. That means you start off at a non-zero initial condition. We want the system to go to 0. Okay, if you are able to do that, the controller has done the job. A good example is what you did in the inverted tandem modeling. So that system, if you don't do anything, you set a non-zero initial condition, you go to infinity, right? That's not good. So in that case, we need to implement a controller to stabilize it. So you can use a state feedback controller to do it. So on Wednesday and Thursday, you will be implementing this on the inverted tandem. Okay, so the goal here, so we back to this, so the system, if you don't do anything, it's called the open loop system. From there, you can derive the open loop poles, right? So the eigenvalues of A will be open loop poles. So again, for a wide variety of reasons, this pole location of the Rogers system may not be suitable, may not be desirable. Maybe it's too slow, maybe it's unstable. In case of the inverted pendulum, you want to change it, right? So you have the open loop poles, which is the blue one, can be anywhere. And then once you insert this control law, you want to change the system such that the poles move to somewhere you want it to be. And you can control this by setting the value of K. Right? Because previously the CE for open loop is SI minus A. So the pole location is only governed by A. And A is like the distribution of the system. So if you like build a robot, it's a parameter of its physical values, like its length, its mass, distance. Unless you want to rebuild your robot, it's actually easier to just implement a controller with K. So it's electronical compensation. You can change the system poles by mechanically changing it. That means you rebuild it. But most people do not do that. They'll build the best and then use the controller to go to the other step. And also, I hope you are aware this is an open loop and closed loop CE. Where the control law is U equals minus K. It's called full state feedback control. Okay, so with this, we talk about how to find K. Because we talk about K, we already know how to find K. So we will now consider the fact that there's no reference input. The goal is to maintain 0 output, as I mentioned before. Right, so as I just derived the expression here, the CD of the system under state feedback control is SI minus A plus BK. Whole thing returned. Okay? And as you remember, the transient and stability of this system under closed loop, under full state feedback is governed by the eigenvalues of A minus BK. Because A minus BK is the A bar, the poles of A minus BK is the poles of the closed loop system. Okay? And now the key right now is to determine what K should it be, or where should you place the closed loop poles. Okay, I think most of you will know that you want to place it as far left as possible, make it fast. And then if you don't want the system to have any oscillation, you want it to have as small of a complex component as possible. I think as you are doing the homework for this week, you will be going through this anyway. Okay, so the key part here is what we're going to focus a little more time is that the problem of placing these poles at the desired location on the left hand plane is what we call a pole placement problem. So you know where you are right now. So you're actually at the blue dots. These blue crosses are the closed loop, the open loop poles of the system. And then for some reason, you don't like it. So you're trying to find a location that you want it. It could be the red location here to make it faster. And to do so, you need to find the K required to bring you there. So there's two steps. One is to identify where to go to. Second is how to get there. Okay. The first question is actually a lot harder to solve. So we'll focus more on the second question, which is assuming you know where to go to, how to solve for the K. Right, so there are 3 steps for pole placement controller design. The first step is you need to check whether you can actually design this controller. We won't spend too much time in this area because this is something I would prefer to cover in greater detail in advanced control if you choose to take it. So in this class, right, we will assume that you can always do it. And why I say this step is important because in certain systems, you cannot design this controller. then you'll be running. How is that possible? And this requires me to go in a longer discussion, so if you're interested to answer this question, you come take overflow. Okay, for now, you just assume that in this class, sure cannot. You can always find this K. Okay? You can always find this K to do this. Second part is the where to place this desired closed pole. This part, you already need to still remember the first order and second order system where if you want the system to have specific time constant, you need to know where to place the pole. Right? Or if for second order system, we have something for the damping ratio and damping frequency. Right? So the output, yes. This is not the same K as the root Lucas. Now don't confuse yourself. This Ki is not the root Lucas K. This Ki is a matrix. It's a vector. There's K1, K2, K3, K4. Root Lucas side, just one K. So this Ki, you note this side is bolded. It's a vector. It is a vector. It contains K1 all the way to Kn. And this N stands for Norway, is the state, the order of the system. So if you're, let's go through the inverted pendulum. If you're set the fourth order, there will be K1, K2, K3, and K4. A lot of things are called gates. This is the full state feedback control gate. Yeah. That K is a different one. Different. There are many gates. There are many definitions in gates. Yeah. It's just that many people like to use K to control. A lot of gates are, even the PID controller, they use K. Yeah, but they use KD, KI, KD. There is no open gate. That's important because your open pose is, if you don't do anything, that is the system response. Closed loop is, you can change it to fit to anything you want. So a good example is the inverted pendulum. The inverted pendulum, right, the open pose is unstable. Right? One of them is on the right hand plane. But if it's like that this way, then the inverted pendulum is useless. You can't do anything. So what you can do is implement a controller such that the closed loop pole of the system is stable. Yes. 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 See this diagram. See? You don't do anything, this is the pole of the system. But once you add in this U plus minus K, the pole of the system has changed. Okay, so one is open loop, no loop inside. Second is closed loop. Okay, for state space, you only learn one controller, which is this. Just remember U plus minus K for state variable control, you cannot be wrong. And then after that, you derive it, you find that the CE for U plus minus K is this form. Right? And then there is the thing. What do you want? You got to do the first loop. That's not the root Lucas. This is not the root Lucas. This is not the root Lucas on this system. It's actually the open loop pole and the closed loop pole. What the root Lucas, if you were to sketch it, is all possible locations of the closed loop pole. The root Lucas is actually a set of lines. Yeah. So don't be confused between root Lucas. And this is actually more of like a pole zero chart, saying where is the pole of the system without closed loop control, which is the blue line. If you don't do any controller, response is governed by the two blue lines, blue axes. Once you implement the controller, this red X side can be shifted to anywhere you want. So normally you want it to be faster, right? So that's why you shift it to the left. You also want it to have less imaginary components so that it's less oscillatory. It can also be the blue dot, the blue cross side is on the right half plane. That means system is by definition unstable. You can use this to pull the closer poles to the left hand side, which is what you do on Wednesday and Thursday for the inverted pendulum. Yes? This is still a vector. For this case, in this example, U is scalar. But U can be a vector. Yes? 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 K can be a square matrix. But again, most of you are starting out. It's very complex to do it all the way. So right now, I assume K is just a vector. There's only one input. And then, if you're running, how do you implement this controller? It's actually very simple. U equals minus K. That means you read the states, multiply by K, and feed it, and that's it. Not answer the question. Can ask again? Okay, so what's the question? What's the value of this k? So this k, if I go back to you, contains k1, k2, k3, all the smaller k's. This k, when you implement it in this form, will cause your system to go from this opener pole, which is the blue one, down like this, to the red color closer pole. So by changing this k, you can shift this red dot location to anywhere you want. This is not a rule, because this is not a rule, because and that k, I say it one more time, that k and this k is not the same k. You remove that connection. This k and the root locus k is different. Again, root locus k is just one scalar k. This is a vector containing k1, k2, k3, all the way to k. Yeah. There is some connection between the two, but not the way you're describing right now. Yeah, so this k, I must say one more time, it's not the same k if you're doing root locus, because many of you are doing homework. It's not the same k. That k is just a scalar k. Okay? This one, this k is a vector or even a matrix k. Right? And this k is called the state feedback control gain. Okay? State feedback control. It's specific for state space system. Root locus, right, is not for state space. You cannot plot a root locus for state space system. You can only plot a root locus for transfer function, single input, single output. You can never plot a root locus for multiple input, multiple output system. It doesn't exist. Okay? And so we are in state space. So state space, this is for multiple input, multiple output systems. Okay, with this, maybe I can go on next. Right? So we talk about first step. We'll check whether you can ever design this controller. In this class, you can always do so. Right? The idea here is if you cannot do so, you cannot find this k. Right? If you have a system that you cannot design this controller, you'll find that when you calculate k, you cannot find k. Okay? But don't worry, in this class, that will not happen. If you're interested to know more, come to 3114, you will learn more about it. Second part is to determine where to place the red color pole. Where to place them. And this has to do with the desired performance specs. Like whether you want the system to be fast, slow, critically damped, over damped, under damped, and damped. This will tell you where to place the pole. Once you do step 2, right, I will focus more on step 3, which is how to find k to meet your requirement. Okay? So the idea is once you know where to place the pole, that means you know the desired closed loop characteristic equation. Design means this is where you want the system to operate. Once you have that, you just need to solve and find the gain k such that your closed loop CE will match the desired CE. Yes. So how to choose the desired pole location? So let me give you a refresher, which is I think useful for your exam anyway. So if you have a first order system, you can choose to place the pole by changing P, right? And then P here will define where on the location of the axis. So if P is small, then it will be close to the imaginary axis. If P is large, it will be like the red line closer to the left hand side. Right? And P and T, now this big T here is the time constant. It's inversely proportional to P. Meaning if you have a large time constant, then P is small. Right? Get it? So if you want the system to be fast, you will have a small time constant, but the P is large. So that's why if you push further to the left, the system will be faster and faster. So comparing the blue line and red line, the system with the closed loop pole and red is faster. And I show you the graph here. The time constant for this one is here, so it's much faster. This one is here. The what thing? So right now there's only one pole. We're talking about one pole right now. One first order system, one pole. But remember, we covered this in first order system. Do you still remember? We covered this in first order system. So the pole location will tell you how fast and how slow. So for example, if your system right now is the blue dot, the blue cross, and you want to speed it up, you will then find that you want to place the pole in the red color location. And the idea here is to find k such that you can get there. Because you already know where to go, K is like sort of like a GPS to get there. Okay? You can think of it as a map. You're here, and then you need to go to there. The K will give you the capability to go from one location to the other. So this is for first order systems, right? For second order systems, then there are two variables you need to be careful of, which is the settling time, not settling, the zeta, damping ratio, and the natural frequency. Right, so two poles can always be written in this form. Right, and I will do the multiple cases. You have the underdamped case and the overdamped case. Let's focus on the underdamped case. Underdamped case. So underdamped is when you have poles on the imaginary plane. Okay, so you can think of it as two poles here and this one here. So imagine your system is the blue one, is the open system, and then you realize, oh, this system is a bit too slow for me. I don't like it. I want to make it faster. Okay, and I'm okay to make it more oscillatory for some reason. Maybe you are trying to generate some energy with this. Then you say, I want the system to be here. Okay? So the system will be faster. When it says faster, that means the certain time will be smaller. Right? So the idea here is you want the system to be here, and then you find a K required to go from this system to here. Alternatively, is you can have your system to be over them. That means you have two poles on the rear imaginary axis, but they're not on each other. This is over them. So maybe, for example, this system is too slow for you, and you want to make it faster, so you actually just want to set the poles to be further to the left, and now you want it to be critically damped. Critically damped is when both poles coincide each other. Here. Right? So then you will find a K to go from the blue color crosses to the red color cross. Okay, I repeat again. So which part? Left side, both side, or okay. So second law system, right? You can break it down into undamped, underdamped, as well as overdamped, critically damped, right? Depending on the value of zeta. So we just focus on underdamped, which is when zeta is between 0 and 1. Right? That is when, if you draw the location of the pole, it will be on the imaginary plane. You have some imaginary component. Once you have a pair of poles that are on imaginary, everything to be underdamped. That means the zeta will be between 0 and 1. So for this system, maybe you say it's a bit too slow, you want to make it faster. So to make it faster, you can push the poles to the left hand side. So then you find a new pole location for this, and then using the method which I'll show later, you will find a K required to go from this blue line to red line. And if you were to plot out what's the difference, so the blue line, the blue cross side will give you a response like this. So setting time is like only 1 second, a bit slow, and then if you want to speed up with this, you will see that it is much faster, less than 0.6 seconds for this one. So by changing K. So again, what I'm going to do later is we're not changing the system, we don't modify the system, we modify the controller. Which is what you all like to do, tune, right? With tuning the controller, you can change this. That is when the system is underdamped. You can also have the system where it's overdamped. Again, both combinations is possible. It's not like left or right. You can have a combination of these two. I just want to show you another example where if your system is overdamped, overdamped means your two poles are real. They're on the real axis, but they're not on each other. And in this case, here, the zeta will be more than 1. In this case, I think 1.5. So maybe this system again, most of the time your system normally is too slow. You always want to speed up the system, and the controller can do it for you. But it's also possible that you want to slow down the system, but the controller can also do the opposite. So that means if your system is too fast, you can speed it up, slow it down by making the poles closer to the imaginary axis. For this example, is we go from overdamped to critically damped. Critically damped is when the two poles coincide each other on the rear axis. And then here, when you have two poles on the same time, zeta is always guaranteed to be 1. So it's critically damped. I think what the question is?
This proposal proof is for the controller only. But I think it's so that means
so actually the open loop closed loop is actually the system. Remember we talked here? Open loop and closed loop.
yeah, but this one doesn't
Why do you say that? Why do you say that? This is space. But the concept is the same.
So it's the same thing as the standard one in Lapa.
So first order, I did first order, I did second order, and then someone was asking me about dominant poles, right? What happens if you have higher order system? Then this is where the dominant poles kick in. The response will be dominated by the poles that are closest to the imaginary axis. Because the poles that are further away are very fast. And if something very fast, right, they don't limit the response. And so if you want to have high order systems, you just find the poles you are close to it, and then you just tackle those two. You only spend more time on the poles that are dominant, which are poles closest to the imaginary axis. It can be a first order or second order, depending. But in this case, the dominant system is a second order, because the two poles are there. And then you can go back to the two steps before and say. So the idea here is any system can be high order, means 3, 4, 5, 6, whatever. But once you have high order, you can always bring it down into combination of first and second order terms. Theoretically. So any high order system, right, is only a combination of first and second order system. The key part right now is you have a high order system, which one is dominant? Is it the first order or second order? Okay, and then I will show you that first and second order. First order system, very important, is the time constant. Yes?
For the previous slide, could you explain how to get the formulas for zeta and omega?
It's in the second order system. Second order system. Check and see. This one, if I remember, is the dot decrement method. You go check and see. Yes. Yes. Okay, yes. The left graph, the right graph. The left graph is red color, it's not higher. Oh, so it's just the location, that means the how much is the zeta. Normally you go higher, the zeta increases. Yeah, the damping ratio. Yes, the question here? So actually, you can go from any combination of this. You can go from these two to here also can. It's not here to here only. You can go from any two pole location to any two pole location. Then the K, which we haven't even gone how to compute the K yet. The key right now, I just want you to identify where you are. That means the system open loop response. And then your desired destination, which is closed loop response. You can yes, you can set your pole to be anywhere you want. So again, your open loop pole is something you cannot change. You agree? The open loop pole is something that's characteristic of your system. When you build it, no matter what you do, the pole is the same. What you have a lot of leeway is to decide where you want the pole to be. That is where you want the system response to be. That's the blue one. The red color one is where you want to be. The blue one is the open loop. So the red one can be anywhere you want. And this one, the location is normally set by your design specification. You want the system to have no damping. You want the system to have a settling time of whatever seconds. All these are design specifications which you set in and tell you where to place the pole. Okay? And then you need to know where you are right now, which is the blue color open loop. You cannot change it. But once you put the system into closed loop, you can electronically change the system response. So if that's okay, then we go on to the final question, which is how to find this K. So you know where you are, which is the blue one, and you know where the red color is where you want to go, how to find this K to get there. Right? So this is the best, is I show you in an example. So I show a very simple state system here. X dot equals minus x plus 0. Anybody can tell me for this system, what's the A and B of the state system? Say again one more time. I rephrase a bit for you. I rephrase because a bit strange the way you describe it. So the system right has two architecture. Let me go back. I think the system architecture. Right, the system right has two architecture. One is last week. No, last week there's no controller. This is up here. So this system I call it overload. And the overload has its own overload characteristic equation. This whole side you cannot change unless you rebuild the system. Okay? You normally cannot change this. I'm saying that right now with state feedback control, if you put the system into this architecture here, this architecture governed by U equals minus KX, it will cause this system to go into what we call a closed loop configuration. Okay? And then the poles in this closed loop configuration is given by Si minus A minus Pk. By changing this K, which I'm going to show you, you can change the desired pole location. Same thing here, if you want to change the CE, you can change A and B, but changing A and B is as good as you changing the entire system. But here, K is an electronical number. It's electronic. This K is U set 1. Do you remember doing the KP, in your controller games in the DC motor? You didn't change the system, right? You just changed the numbers only. But doing so, you can change the response of the system. That's why electronic control is very useful. You don't need to do any hardware change. It's pure software. And same thing here. For state feedback control, you can change the response and stability of the system first by changing K. Because it changes the closed loop CE in this manner. How about we do an example? You do an example, I think it's easier to understand. So here I have a very simple example here. I ask you for this system, what's the A and B? So I'm sure you can tell me A is -1, B is 1. So it's a super duper simple space system. Can you tell me for this system without control, what's the CE of this system? Don't forget you told me already, it's Si minus A, right? So you substitute in, you get here, S plus 1 equals 0. Right? And then this leads on to the next question, what's the pole of the system? You solve the CE, you get S equals minus 1. Is this system stable? Yes, because the pole is on the left half plane, right? Now we try to connect with the material that you learned previously. Can you tell me, if you know the pole location, what is the time constant of the system? No. It's when the cogs, I can see your cogs trying to move. I help you a bit, I already give you a primer here. So if you know the pole location, which is P, the time constant is the reciprocal of the value, which is what? 1 over 1 is still 1. So the time constant of this system is 1 second. Right? 1 over 1 is 1 second. So that means this system will take 1 second to reach 63.2% of its final value. Because that's the definition of the time constant. To reach 63.2% of the final value, time constant. So do you think this system is fast or slow? So let's say I say it's very slow. That's where we come to the last part here. Design a state feedback controller such that the system now responds 5 times faster. Okay? So you can see this part here, actually this sentence here actually tells you a lot. So I'll try to decompose it for you. I will erase this part, okay? I need this space. Okay, so this is the S-plane. Let's do some graphical illustration. I'm going to now plot the open loop pole system. How many poles are there? 1, right? So can you tell me where I should put a cross to mark out the open loop pole? Where should it be? Where should it be? Left side at negative 1. So this is the open pole, right? And it's at -1. This question says that this system is too slow. I want the system to be faster. And then it's not just faster, it says quantitatively, 5 times faster. So now, let's see. Let me see which is the best way. There's a calculative way to do this. You use the pen to calculate. The other way is there's a visual way to do it. Which one you want to see first? Visual way or mathematical calculation way? Which one you want to do? I will decide. We do the visual way first. Okay. So let me help you to understand. If you still remember your root locus or S-plane line, this part here is the setting time. Right? The distance to the imaginary extent is how fast the system sets up. Do you agree? So this is this thing. So if you want the system to be 5 times faster, then how? Maybe you answer the first question. Should the pole move to the right hand side? Or the pole move to the left hand side? You think about this part first. If you want the system to be faster, the pole needs to be on the left, right? Very good. Now, how much to the left such that I get 5 times? I already told you that this distance here is this guy's setting time. But this side, this distance represents this setting time. So if you want it, and you already told me going to the left is faster. Right? You already told me going to the left faster. So this is -1. If you want to go 5 times faster, if I draw a red cross, where should it be? So if I draw a red cross, right, what should it be? I know it's somewhere here. No question. I just need you to tell me where should it be. -5. Right? Because then here is the setting time. Again, this one doesn't mean larger setting time, it's actually smaller. But this is 5 times. -1 times 5 is 5. That's one way to find out. The other way is, if you don't like this method, you can find out the time constant. So the time constant for this system here, so the time constant for this system here is 1 second. Right? So if you want the system to be faster, so this is the, maybe I do, this is the open loop, and then now I calculate. Can you tell me if you want the time system to be 5 times faster, so what should the time constant be? So you want the system to be faster. Time constant should increase or decrease? You look here. So this one 1 second. We found that this is 1 second. Can you tell me if you want to make it 5 times faster, what should the time constant for this system be to be 5 times faster? The time constant should be 5 times smaller. So 1 divided by 5 is 0.2, right? So this will be 0.2. Right? And then the P is 1 divided by 0.2, which is 1 divided by 0.2 is 5. Then you get back to that. Okay, so you can calculate this either visually, 5 times, or you calculate the time constant, then you calculate where it should be, and you tell you that it's the same equation. Okay, so again, this is your current system. This is the pole location. This is where you want the system to operate. You want the pole to be at -5. The key question right now is what K is needed such that you get there, right? So the desired time constant is 105.25, right? Same thing. So that means your desired pole location is -5. So far so good? Yes?
Why is -5 though? Like that's very arbitrary. Or why you chose 5 instead of like 4 or 6?
It's a question. Yeah, you're right. It can be any question. It can be any number. I just give you 5 so that you get something to base on. Yeah. There's no special reason why it's 5 times. It's just so that you have something to discuss. I mean, I could put it x time. Then it's harder. 5 is a number at least we can look at.
Paul, so the settling time is not actually 1 second, right? It's just the representation.
Yeah, so actually, this one here, this thing here actually is 4 divided by zeta omega.
Which represents my settling time.
It represents the settling time, but actually is 1 over, roughly. Because this value, the setting time is 4 over zeta omega. Sorry, I misunderstood. This value here is zeta omega. And then your setting time, right, is about 4 divided by zeta omega. So this number here is not really, how do I say it? You don't actually read this and find the setting time. It's approximate, but it's related to. Because if you remember, if you were to find the locus of all constant setting time is a vertical line. Yeah, this was second order. Okay, fine. You want to do that? Can. This is in general, because I did sentence. Okay. So then this one will be 1 over t, right? Yeah, 1 over t. For first order student, it's 1 over t. So this one is the t open loop, this is t closed loop. Better? Really nice, better. Then it's numerically correct now. Because now zeta omega is for second order stuff, but I rephrase it for first order. So setting time is 1 over t only. Okay. So with this, can anybody tell me? So we established that the current pole, the current CE. Yeah, erase this part. So I'm going to write a sequence of equations here. So right now the current CE is what? Can you tell me what's the current CE? Means the system right, without any controller modification. What will it be? So it will be S plus 1 equals 0. Okay? Right, this is the current system pole. Now I want you to go into what is the desired closed loop CE. Yes. Okay. That's completely correct. Okay. So can anybody tell me, now that we calculate this, can you tell me what is your desired CE such that your system has a response 5 times faster? S plus 5 equals 0. Right? So this is the desired CE. Yes? Anybody agree with this? So we have the current CE, no controller, is 1 plus S plus 1 equals 0. And then we define that if you want to make the system 5 times faster, you will have a desired CE of S plus 5. So the key question right now is we need to find a way to find K such that our desired CE is S plus 5. Anybody can remember what's the expression for the desired CE when it's under state feedback control? Si minus A bar, right? And I will rewrite this for those who want to see the full expression. Technically, it's Si minus A plus BK. Okay. So then we have our closed loop CE under full state feedback control. This is Si minus A plus BK. Determinant set to 0. This equation, do you know A? Do you know B? You know K? No, right? But that's what you try to calculate. You agree? So this, the last part here is to realize that these two should be equal. Then you can find K. So this one describes the closed loop CE of the system under full state feedback control. This one says that where you want the system to be at. So the goal right now here is to find K such that when you insert this thing here, it becomes S plus 5. So A is -1, B is 1, you substitute in. K is just one value K1, because there's only one state here. So this is the first order system. This K, right, has only one K, which is K1. And this is the first order system. The K, right, is a function of how many states there are. This system only has one state. So to do this, we can go on and see what's next. So you multiply out. Right, so feedback gain is K equals K1. The control law is U equals minus Kx minus Kx, K1x. Substitute into that equation here. Si minus A plus Bk. So A is -1, B is 1, you multiply out, you get this. S plus 1 plus K1 is 0. You want it to be S plus 5, right? You see that? You need it to be S plus 5. So in order for that to be so, you can solve that K1 must be 4. Okay? And then if you were to plot out, this is actually the system. So the system, the response initially was this blue, right? And then once you put this U plus K, the system will respond 5 times faster. If you implement this simple controller, it just takes the U, multiplied by the current state x, multiplied by -4. And that's your controller. Just that simple controller will make the system 5 times faster. Okay, anybody got any questions? So I'll bring it down for you. So you have the system current response, which is governed by the current poles of the system, which is at -1. So the system is relatively, I would say, slow. But the time constant is 1 second. So we're not happy with this response. We want to make the system faster. You can also make it slower if you want. But for now, for this example, we want to make it faster. And then we decided that we want to make it 5 times faster. This 5 can be something that is dependent on the question. You can calculate for 10 times, up to you. Then the desired pole location will change, and then the K will change accordingly. So as you can see, if you want to change it 5 times faster, you will first calculate where you want the pole to be. Right? So we decided that we found that the current pole is -1, too slow, we want to move it to -5. To do so, we need to find K to move it there, and this is where you find Si minus A plus Gk, which is the general form for the system under full state feedback control. This is the CE. We try to match these two. And when you find that, the only way for that to happen is when K1 is equal to 4. So, for those who are looking at this question, you can also say you want to make the system 10 times faster. For example, if you want to move it 10 times faster, then this will be -10. And this will be +10. And then your K1 will be 9. Okay, so depending on where you want to operate, the gain will change accordingly. You can also make it slower. You can say that maybe 1 second is too fast. You can make this to be 0.5. You can slow it down also. Then the gain will change accordingly. FSS, full state feedback control. Full state feedback, FSS. So this is a first order example. That means where the system is first order. I won't do it today. Tomorrow we'll go through second order example. So this is the second order system where, so this is the A and B of the system, and then it says design a full state feedback controller for this second order system such that the poles are at -2 branching. And then say confidence. We'll continue this tomorrow. I don't think I want to finish up today. But the form, the concept will be the same. You will first find the CE of the current system, right? Then compute where should the desired CE be for the system. Compare it to this general form, and then find K. In the second order example, there will be K1 and K2. That's the only difference. So if your system third order, there will be K1, K2, K3. For the fourth order example that you'll be doing this fancy, say for the inverted pendulum, there will be K1, K2, K3, and K4. So
characteristic equation. It has to be quick.
and so before we end up for today, any questions
Logically, I don't see
for full state feedback control, which is a controller synthesis method for state feedback system. State space system.
minus 5 and that makes sense. Oh, yeah, I think I know.
As in mathematically, because you are sorry for your.
I think I got it.
If not, we will see you tomorrow. And then this week we will complete the last lab where you will implement a full state feedback controller for the inverted pendulum. And then you will see the system automatically stabilize.
What did you do? S minus 5.
Okay, then we'll see you tomorrow.
So when I shift this over, it becomes
That's
minus 3
also mathematics.
plus 3k equals to 5. Then I plus S from